Alright, so the first thing we're going to do in this video about graphing exponential equations is to talk about getting the equation from the graph first, like we did last time where we had the points and we found the equation. And then we're going to go the other way around today. We're going to look at, if you are given the equation, how do you get the graph? We've got a lot of experience with that already with quadratics and with linear, so I am going to do my best to try to keep this lesson a whole lot shorter and sweeter, so to speak. So let's first of all, though, take a look at a little bit of review here with this, finding the equation of this scatter plot, this set of points. So I'm going to go to my Desmos graph here. I'm going to hit on the plus little sign here and get table. And then I'm going to type in my values that I have here for x, -3 all the way up to 2 there. So I'm going to type in -3, -2, -1. Notice Desmos automatically starts to put the next one in for me. So Desmos has a pretty cool little feature like that. If it starts to notice that you're using a little bit of a pattern there for your x values, going up by 1 every time, it helps. All right, so then we're going to take a look at 50, 25, 12.5, and then we're going to look at 6.25, 3.13, and then we're going to look at 1.56 here. If we type in those points, again, this little plus zoom fit right here helps me to zoom in on the points. I can see that this has my distinctive exponential decay curve, like we talked about on the writing exponential equations video. Notice that it is not linear. It's not a straight line. It's not quadratic. It doesn't make a U shape. It's tempting when you first start looking at one side of this to say it's a quadratic, but then notice it levels off. And we're going to talk about why that is on the graphs of these today. So last time what I showed you is you can find an equation for these if you know the basic shape of a exponential equation. All you have to do is type in y1, and instead of putting equals, you put this little squiggly little equal sign. Basically, it's an approximation sign. It's right there beside the 1 at the top of your keyboard. Then we do a times b raised to the x power, because that is the basic format of an exponential function. Remember, we talked about it could be 1 plus the rate or 1 minus the rate. The calculator, though, will figure out what it is for me for that b value on the inside. And then I'm going to raise it to the x1 power. You do have to hit the little x1 so it knows you're talking about the table. Notice it graphs that line also for you, or that curve, I should say. You have your a of 6.25 and your b of 0.500013 right there. So essentially your equation for this is y equals 6.25 times 0.5 raised to the x. So this one is cutting in half every time. That means this is a 50% decay. Notice I know that because it's going down, number one, and because this number right here inside the parentheses is less than 1. We talked about that in the video last time as well. The little tricky part about this, and it might confuse you a little bit here, is you got this 6.25. Remember, we talked about that being our beginning amount. Notice that is the same thing as this 6.25. Now, if your points are not as pretty as these, you will sometimes see it. It's not perfectly matching that number, but it will be close to whatever that number is in the middle of the graph there at 0. Why is that? The beginning amount on this problem seems like it should be 50 over here. But remember, in mathematics, when we graph the equation, the beginning amount is actually the number that is at the y-axis, the y-intercept. Just like what we did with linear functions and quadratic functions. The y-intercept, the place where the graph crosses the y-axis, is the part where our graph in real-life context begins. Now, in this particular mathematical sense, yes, there's other points to the left over here. But that middle point is the point at 0. That's on the y-axis. That's my beginning amount. So We'll talk about that in a little bit more detail in the graphs here in a second. Real quick before we do that, I want to make sure we understand the difference between growth and decay. Remember we talked about growth having a number that's bigger than 1, decay having a number that's less than 1. So this one here would be growth. This one here would be decay. This one over here, 5/6, is actually still less than 1. That would also be decay. The only ones I want you to be careful of is when you have a negative x for your exponent, that means it's going to take the opposite of x when you plug it in, and it's actually technically going to flip it and make this thing opposite of what you think it is. Instead of growth, this first one right here would actually be decay, and instead of decay, this one here would be growth. I just want you to be aware of those situations. There are a few weird ones like that, but for the most part, whenever you have a number that's bigger than 1 here, it's growth. When you have a number that's less than 1 here, it's decay. As far as me actually having to graph it, what I do is just like what we did with linear equations and with quadratics. Now we got a little more specific with quadratics because we wanted to find a particular point called the vertex. Remember, the vertex was really important for us. With exponential functions, you don't have a vertex, so you can treat them just like you did linear functions by plugging in a value for x and plugging in -2 and -1 and 0 and 1 and 2 is going to be the easiest ones to plug in. Then it's just taking out your handy-dandy calculator, just like we did the other day in the writing equations section when we looked at plugging in a number for x in our bank accounts and figuring out, and look at me what I'm doing here. I'm being goofy here, trying to talk and do this at the same time I messed up that time. Plugging in a number for x right here. Golly, guys, I am struggling on this part. It happens to the best of us, right? All right, let's try this again. There we go. So when we plug in a number for x, what it is doing is it is giving me a y value as my output. So just like we did with linear equations, we're just plugging the number in the calculator and getting an answer. We did this the other day, like I said, and like I was talking about with a bank account when we plugged in a number for the years in our bank account to figure out how much money we would have. So you would just go to the calculator if you need a calculator, and you would type this stuff in. You would go, okay, I'm going to do 4 times 2, raise that to the -2nd power, and it gives me 1. Then I'm going to do the same thing again, but this time I'm going to raise it to the -1st power. That gives me 2. All right, then I'm going to raise it to the 0 power. If I raise it to the 0 power, notice what's going to happen here. This is what we talked about a minute ago. It gives me 4, the beginning amount. Because when you plug in 0 for this basic exponential function, you're going to see that it gives you the beginning amount, because that is what happens on the y-axis at 0 for x, even in linear equations and quadratics as well. So you just keep on going. This one's going to be 8, this one's going to be 16, and you're going to see that these points right here are doubling every time because of the 2 inside the parentheses. Now again, we've used that several times on the last video. We talked about things that are doubling. We've used it and talk about things that are cutting in half, like this guy over here is going to do. Guys, that's not the only types of exponential functions that you have to graph. Remember, you could have a bank account that's 1.065, like we did last time, inside that parentheses. So it's not going to change what you do, though. You just plug in the numbers, you get the y values, and then you're plotting the point. Now, what I'm going to do here is I am going to graph these sort of with just me kind of sketching an axis, and I know that's not going to be the prettiest thing because you got Mr. Harrison's handwriting and drawing skills are not always the best. I realize that. You probably realize that now, right? And so we've got these numbers here. We got -2, or -1, 0, 1, and 2. And then we've got all these numbers up here. Now, I'm only going to go up to 8 here, so I'm not going to be able to put my other 216. But -2, 1 would be the point here. -1, 2 would be the point here. 0, 4, notice that's my y-intercept, and that's my beginning amount right there we talked about. And then 1, 8 is up here. 2, 16 would be way up there somewhere. This graph, if you were to keep going this way, and I'm not going to do this, but if you were to keep plugging in -3 and -4 and -5, what's actually going to happen is, think about the way these graphs are doubling every time. What would happen if you're going backwards, if you're thinking backwards, is it be cutting in half every time. And so what happens is we get this ramp shape like we talked about that looks like it's kind of leveling off, but it doesn't ever get to 0. Think about it, guys. If you raise 2 to a power x, no matter what you plug in for x, it'll never be 0 because you're raising 2 to a power. It may get really, really small, so small that you can't even see the difference between the line and the axis, but it will never touch the axis because it's just going to keep cutting in half every time we go this way. So that is why these graphs have something that we call an asymptote. I'm going to say that word again. It's kind of a weird word, but these graphs have what we call an asymptote. What that means is the graph approaches closer in distance to this thing, but it doesn't touch it. Now, there are some graphs and some uglier functions later on you may look at in Algebra 2 that have asymptotes, and you have some asymptotes that actually do get touched. But for the most part, most of your functions that have an asymptote, it means that this line, this curve, is getting closer and closer and closer down to 0 because it's cutting in half, but it doesn't touch it because it keeps cutting in half. It just gets closer and closer and closer, but it doesn't touch it. And so what we talk about as an asymptote is a line that the graph approaches. So this is how you graph an exponential function. You make a table of values, you plot the points, and you realize that at some point it's going to level off. If you don't have any number over here that's added or subtracted to the function, you will have the asymptote on the x-axis. But there are some times when you will run into a function that has a number that is added or subtracted over here and added or subtracted here. I hope that you can kind of recognize those two letters right there because they're very similar to something that we did with quadratics called Vertex Form. Let me give you an example. We'll use 4 times 2 to the x like we did a minute ago, but this time we're going to put x minus 1 and x plus 3 over here. Now, if you look at that, the original function that we just did was 4 times 2 to the x. That's still the same function we're looking at, but this minus 1 and this plus 3 are doing basically the same thing that they did when we were dealing with quadratics. Remember when we took the opposite of the number that was on the inside with x, and we took the same as the number on the outside that was added, and that was our vertex? It was called Vertex Form for a reason. Well, guys, it's the same concept here, but the reason it's the vertex in a quadratic was not because it's just a magical formula. It's because what it literally does is move the function. So guess what? This minus 1 and this plus 3 will take the function that we just looked at and it will move it. Now, I'm going to go back over here and I'm going to see if this thing will let me copy. I hope it will let me do that. Let's see if we can do that. Oh yeah, look at there. Fancy, huh? All right, so that right there is my original function. The minus 1 and the plus 3 is going to do opposite same, and it's going to move this graph to the right 1 space and up 3. It's always the opposite of the one with the x. So my suggestion, whenever you run into an uglier exponential function is not to try to graph the whole thing and try to type all of this into the calculator. If you try to type all of that into the calculator, it's going to be ugly, but you can still do it. I'm not saying you can't. It's going to be easier if you take this little guy right here, graph him like we did a minute ago, and then move every single point right one space and then up 3. 1, 2, 3. And what it does is it takes this entire graph, right 1, up 1, 2, 3. Right 1, up 1, 2, 3. Right 1, up 1, 2, 3. And it moves my entire graph up 3 spaces and over right 1. And so what that also means is it takes my asymptote that we have here and it moves that up 3 spaces too. So I have this asymptote that's moved. I like to kind of joke here a little bit. Sorry, bad math teacher joke, but you got to move your asymptote. Some of you'll get that later probably. But seriously, guys, you take this and you slide the whole graph right 1 and up 3. The right 1 is not going to change the asymptote. It's the up 3 that changes the asymptote. So all you have to do is be able to plug in a table of values like we did over here, like we've done numerous times with linear and quadratic functions. Get your points and plot them. If there is a -1 and a +3, if there's more stuff in the function, so to speak, then you just take the graph and move it right 1 and up 3. Please make sure you realize, though, that's me plugging into this part right here. Don't plug it into the whole thing and move it right 1 and up 3. Make sure when you do that right 1 up 3 that this is what you plug your table of values into. Just the one little tiny part we did is what you plug in your table of values to. So that is graphing an exponential function. Last thing I want to show you is be careful with ones like this, because if you see this 3 right here, it is supposed to be exponential growth. But if I make my table of values, I might panic, because if I start plugging in these numbers, what I'm going to notice is that I'm going to end up right here with -2/9. That's a decimal. Yes, you can get a decimal. -2/3, 0.67 right there. -2, -6, and -18. What's happening there is I've noticed that this graph would end up doing this little number right here, because it would be going through here at -2, and it would go down to 1, -6, and then 2, -18 would be way down here. A lot of people look at that and say, that's decay. It's going down, but it's supposed to be growth. Actually, it's still considered growth. Even though that looks kind of weird, that is growing away from the y-axis, away from the asymptote as the x gets bigger. Think of it this way. The national debt is growing, but it's growing in a negative direction. It's not a good thing, but that is the same concept here when we talk about this graph still being growth. So to make a graph of an exponential function, I'm going to review it again. Make your table of values for the basic exponential function. If that's all you got, connect the dots, you're done. Just remember there is this thing called an asymptote here. Then, if there's more stuff involved, if you got a -1 and a +3, you still start off with the basic not absolute value, the exponential function here. Then you move it the same way that we did when we were talking about quadratics. I know this says radicals because I forgot to change it from the thing that I do with my order of my Algebra 1 and Algebra 2 students in other years. So that's how you graph an exponential function. If you got any questions, don't hesitate to get online and ask me. Don't hesitate to set up a time to meet with me.